Now, there's one more type of search for plans that we can do with the classical planning language that we couldn't do before. And this is searching through the space of plans rather than searching through the space of states. In forward search, we were searching through concrete world states. In backward search, we were searching through abstract states in which some of the variables were unspecified. But in plan space search, we search through the space of plans. And here's how it works. We start off with an empty plan. We have the start state and the goal state, and that's all we know about the plan. So obviously this plan is flawed. It doesn't lead us from the start to the goal. And then we say, let's do an operation to edit or modify that plan by adding something in new. And here we're tackling the problem of how to get dressed and put on all the clothes in the right order. So we say, out of all the operators we have, we could add one of those operators into the plan. And so here we say, well, what if we added the put on right shoe operator? And then we end up with this plan. That still doesn't solve the problem, so we need to keep refining that plan. Then we come here and say, well, maybe we could add in the put on left shoe operator. And here I've shown the plan as a parallel branching structure rather than just as a sequence. And that's a useful thing to do because it captures the fact that these can be done in either order. And we would keep refining like that, adding on new branches or new operators into the plan until we got a plan that was guaranteed to work. Now this approach was popular in the 1980s, but it's faded from popularity. Right now, the most popular approaches have to do with forward search. Now we saw some of the advantages of backward search. The advantage of forward search seems to be that we can come up with very good heuristics. So we can do heuristic search, and we saw how important it was to have good heuristics to do heuristic search. And because the forward search deals with concrete plan states, it seems to be easier to come up with good heuristics. To understand the idea of heuristics, let's talk about another domain. Here we have the sliding puzzle domain. Remember, we can slide around these little tiles, and we try to reach a goal state. 16 puzzle is kind of big, so let's show you the state space for the smaller 8 puzzle, and here's just a small portion of it. Now let's figure out what the action schema looks like for this puzzle. So we only need to describe one action, which is to slide a tile T from location A to location B, and the precondition, the tile has to be on location A and has to be a tile. And B has to be blank. And A and B have to be adjacent. That should be an and sign, not a A. So that's the action schema. Oops, I forgot. We need an effect, which should be that the tile is now on B, and the blank is now on A, and the tile is no longer on A, and the blank is no longer on B. Now we talked before about how a human analyst could examine a problem and come up with heuristics and encode those heuristics as a function that would help search do a better job. But with this kind of a formal representation, we can automatically come up with good representations of heuristics. So, for example, if we came up with a relaxed problem by automatically going in and throwing out some of the prerequisites, you throw out a prerequisite to make the problem strictly easier, then you get a new heuristic. So, for example, if we crossed out the requirement that B has to be blank, then we end up with the Manhattan or city block heuristic. And if we also throw out the requirement that A and B have to be adjacent, then we get the number of misplaced tiles heuristic. So that means we could slide a tile from any A to any B, no matter how far apart they were. That's the number of misplaced tiles. And other heuristics are possible. For example, one popular thing is to ignore negative effects. to say, let's not say that this takes away the blank being in B. So if we ignore that negative effect, we make the whole problem strictly easier. We'd have a relaxed problem, and that might end up being a good heuristic. So because we have our actions encoded in this logical form, we can automatically edit that form. A program can do that, and the program can come up with heuristics rather than requiring the human to come up with heuristics. Now I want to talk about one more representation for planning called situation calculus. To motivate this, suppose we wanted to have the goal of moving all the cargo from airport A to airport B, regardless of how many pieces of cargo there are. You can't express the notion of all in propositional languages like classical planning, but you can in first-order logic. And there are several ways to use first-order logic for planning. The best known is situation calculus. It's not a new kind of logic. Rather, it's regular first-order logic with a set of conventions for how to represent states and actions. I'll show you what the conventions are. First, actions are represented as objects in first-order logic, normally by functions. And so we would have a function like the function fly of a plane and a from airport and a to airport, which represents an object, which is the action. Then we have situations, and situations are also objects in the logic, and they correspond not to states, but rather to paths, the paths of actions that we have in state space search. So if you arrive at what would be the same world state by two different sets of actions, those would be considered two different situations in situation calculus. We describe situations by objects, so we usually have an initial situation, often called S0, and then we have a function on situations called result. So the result of a situation object and an action object is equal to another situation. And now, instead of describing the actions that are applicable in a situation with a predicate actions of S, situation calculus for some reason decided not to do that. And instead, we're going to talk about the actions that are possible in a state, and we're going to do that with a predicate. We have a predicate possible of A, and S is an action A possible in a state. Now, there's a specific form for describing these predicates, and in general, it has the form of some precondition of state S implies that it's possible to do action A in state S. I'll show you the possibility axiom for the fly action. We would say, if there's some P, which is a plane in state S, and there's some X, which is an airport in state X, and there's some Y, which is also an airport in state S, and P is at location X in state S, then that implies that it's possible to fly P from X to Y in state S. And that's known as the possibility axiom for the action fly. Now, there's a convention in situation calculus that predicates like at, we said plane P was at airport X in situation S. These types of predicates that can vary from one situation to another are called fluents, from the word fluent having to do with fluidity or change over time. And the convention is that they refer to a specific situation, and we always put that situation argument as the last in the predicate. Now, the trickiest part about situation calculus is describing what changes and what doesn't change as a result of an action. Now remember, in classical planning, we had action schemas where we described one action at a time and said what changed. For situation calculus, it turns out to be easier to do it the other way around. Instead of writing one action or one schema or one axiom for each action, we do one for each fluent, for each predicate that can change. And we use a convention called successor state axioms. And these are used to describe what happens in the state that's a successor of executing an action. And in general, the successor state axiom will have the form of saying, for all actions and states, if it's possible to execute action A in state S, then, and I'll show in general what they look like here, then the fluent is true if and only if action A made it true, or action A didn't undo it. So that is, either it wasn't true before and A made it be true, or it was true before and A didn't do something to stop it being true. For example, I'll show you the successor state axiom for the in predicate. And just to make it a little bit simpler, I'll leave out all the for all quantifiers. So wherever you see a variable without a quantifier, assume that there's a for all. And what we'll say is it's possible to execute A in situation S. If that's true, then the in predicate holds between some cargo C and some plane in the state, which is the result of executing action A in state S. So that in predicate will hold if and only if either A was a load action, so if we load the cargo into the plane, then the result of executing that action A is that the cargo is in the plane. Or it might be that it was already true that the cargo was in the plane in situation S, and A is not equal to an unload action. So for all A and S for which it's possible to execute A in situation S, the in predicate holds if and only if the action was a load, or the in predicate used to hold in the previous state and the action is not an unload. So I've talked about the possibility axioms and the successor state axioms. That's most of what's in situation calculus, and that's used to describe an entire domain like the airport cargo domain. And now we describe a particular problem within that domain by describing the initial state, and typically we call that S0, the initial situation. And in S0 we can make various types of assertions of different types of predicates. So we could say that plane P1 is at airport JFK in S0. So just a simple predicate. And we could also make larger sentences. So we could say, for all C, if C is cargo, then that C is at JFK in situation S0. So we have much more flexibility in situation calculus to say almost anything we want. Anything that's a valid sentence in first order logic can be asserted about the initial state. The goal state is similar. We could have a goal of saying there exists some goal state S such that for all C, if C is cargo, then we want that cargo to be at SFO in state S. So this initial state in this goal says move all the cargo, I don't care how much there is, from JFK to SFO. Now, the great thing about situation calculus is that once we've described this in the ordinary language of first-order logic, we don't need any special programs to manipulate it and come up with a solution, because we already have theorem provers for first-order logic, and we can just state this as a problem, apply the normal theorem prover that we already had for other uses, and it can come up with an answer of a path that satisfies this goal, a situation which corresponds to a path which satisfies this, given the initial state and given the descriptions of the actions. So the advantage of situation calculus is that we have the full power of first-order logic. We can represent anything we want, much more flexibility than in problem solving or classical planning. So altogether now, we've seen several ways of dealing with planning. We started in deterministic, fully observable environments, and we moved into stochastic and partially observable environments. We were able to distinguish between plans that can or cannot solve a problem. But we had one weakness in all these different approaches, is that we weren't able to distinguish between probable and improbable solutions. And that will be the subject of the next unit.